Hello, everyone out there. This is Dan Sperling. I'm have my video turned off because I'm in a place with bad internet. I'm in Los Angeles, less civilized place of the world. And so I want to welcome, and this week we have someone that's really special. And I should say also, I'm having internet connection, so Susan Handy will hopefully jump in if there's any problems. So let me just jump right in and introduce our speaker, David Greene. So I've known David a long time, and David Greene is, I can say this with complete confidence, has been the premier, the best transportation energy analyst in the US for the last 30, 40 years. And he has been the one that's played a central role in making sure research is brought to policy, especially on fuel economy standards, which he's going to talk about today. I could tell lots of funny stories about David, but I won't embarrass him this time. David did spend a year with his wife in Davis about 10 years ago. He was on sabbatical with us. He spent most of his career at the Oak Ridge National Lab, where he was one of their top scientists. And he's actually brought in one of our recent graduates. He mentored and brought to Oak Ridge from our TTP program. And so this is really, we're very fortunate to have David here. He left Oak Ridge National Lab, or I guess he has some affiliation, but is now affiliated with the University of Tennessee at Knoxville. So David, and maybe for the benefit of the students, give just a few words about your history, because a lot of students are trying to figure out, what's the right pathway, and they've heard it many times now, but the real lesson is there is no one pathway, and there's many different paths. So you'll add to that storyline, I know. So David, take it away.
Okay, thank you very much, Dan. That's the best introduction I've ever had. So I appreciate that very much. And good afternoon, everyone. It's a pleasure for me to be back at UC Davis, even if it's just virtually. I enjoyed my stay there very, very much, working with outstanding researchers, and it was a great time for me. And I want to return Dan's compliment by saying not only am I a huge Dan Sperling fan, but in my opinion, the ITS Davis, which he created, is the world's leading institution as far as sustainable transportation research, and that's saying something. So my career, well, after finishing my PhD in geography and environmental engineering, I took a job at Oak Ridge National Lab. I thought I would leave after 2 years. You think you're supposed to teach, but I stayed for 36 years with some time in Washington, DC at the Department of Energy and a year at UC Davis. And now I'm at the Howard Baker Center for Public Policy at the University of Tennessee. I think my credentials on fuel economy and regulation are pretty good. There have been so far 5 National Academy committees on the subject. I'm the only person who's been on all 5. I say they're going to keep putting me on until I get it right, but whatever their reasoning is, I have a lot of experience in this field going way, way back to the early days of the standards. And so that's what I want to talk about today. I've put this graphic from fueleconomy.gov website on the title slide, just to remind us that there's a lot more to the energy efficiency of a motor vehicle than the internal combustion engine, although that's a really important part for internal combustion engine vehicles. And also, I just want to mention, I'm going to talk about light duty vehicles today. There are important greenhouse gas standards for medium and heavy duty vehicles, and I'm just not going to cover them in today's talk. Ooh, there we go. So I like this quote from the Global Energy Assessment, which I think is the most comprehensive look at how to get the world to a sustainable energy system. And they concluded that the single most important area of activity was energy efficiency improvement across the entire economy. Of course, it's a whole transformation that we're trying to do to get to deep decarbonization. It's a system transformation problem, which is really complex. And I'll eventually get to talking about what role fuel economy standards could play in that. But first, I'm going to talk about what they are, and then about what they've accomplished and how that happened, and then why they seem to work. And they seem to work very well, in my opinion. And then touch on some of the leading unintended consequences that people have raised for fuel economy standards. And then finally to my main point, which is, okay, where do we go from here? So US corporate average fuel economy standards and greenhouse gas standards are what many people call technical performance standards. They require a business to meet a definite quantitative criteria, but they don't say how they have to do that. They don't specify that. And they usually allow some averaging across differentiated products. So when the first standards were first formulated, companies could average across all their vehicles within the passenger car segment and all the vehicles within the light truck segment. So that's the corporate averaging. And they sometimes allow manufacturers to earn credits in a given year for exceeding the standard, carry them forward to offset a shortfall in a future year, or even backwards to cover a historical shortfall. And that's temporal averaging. And very often they allow manufacturers to buy and sell credits among themselves, so industry-wide averaging. And the whole point of that is to equalize the cost of meeting the standards, the marginal cost of meeting the standards, and that has a property of increasing their efficiency. So when standards are binding, that is when they change the way a manufacturer makes their products compared to what they otherwise would have done, they're like a tax on the regulated criterion. So in this case, greenhouse gases, let's say, because the standard induces what economists or math programmers call a shadow price. It's equivalent to a tax on what is being regulated that increases with the deviation from the standard. And there are lots of examples of technical performance standards, even in other sectors. SO2 standards for power plants and so on. But both the CAFE and greenhouse gas regulations, tailpipe emission standards for motor vehicles, low carbon fuel standards is a technical performance standard, and even ZEV mandates can be looked at that way. So what's the history on this? The standards were passed in December of 1975 in the Energy Policy and Conservation Act. And they said, every manufacturer has to increase the fuel economy of its vehicles to 27.5 miles per gallon by 1985. The passenger cars at that time were getting about 13.5 miles per gallon, pretty bad. And the light truck standards were separate and to be set by rulemaking by the National Highway Traffic Safety Administration. So first of all, we call them fuel economy standards, but in fact, they're based on the sales weighted harmonic mean of fuel economy, which is essentially the mean of gallons per mile, not mean of miles per gallon. So they're really gallons per mile standards when you get right down to it, mathematically anyway. And they were separate car and light truck standards. There were credits for exceeding the standards. They were transferable within a manufacturer's fleet of cars and passenger trucks, but not between those fleets and not with other manufacturers. And you could carry forward the credits 5 years or carry them back 3 years. There were concerns about the standards initially, first because of their equity and efficiency, the way that affected a manufacturer had to meet a standard regardless of those kinds of vehicles it made. So if you were a US manufacturer and you had a full line of vehicles from small cars to large cars, it's much tougher for you to meet the standards than what was happening at the time was many vehicles coming into the United States, early products from Asia and from Europe. They were generally smaller and had higher fuel economy than the US products. And so the impact was mostly on the domestic manufacturers. And there were also concerns about highway safety because in the original standards, they anticipated that a large part of the fuel economy improvement would come from making cars smaller, lighter, and not necessarily just from improving technology. So Changes were made over the years. NHTSA, the National Highway Traffic Safety Administration, in 2003 said light trucks standard will be now indexed to the footprint of the vehicle, which is the distance from the front axle to the rear axle times the distance from one tire on the left side to the tire on the right side, essentially that rectangular, which is the footprint of the vehicle on the ground, meaning that if you made big vehicles, you had a easier standard to meet than if you made a lot of small vehicles. And then in 2007, the law was changed to index passenger cars as well. And then also in 2007, they said, okay, there's going to be credit trading among firms. You can buy and sell credits among yourselves, and also you can exchange them between your car and truck fleets. All things designed to make it more efficient. So what happened? Well, by and large, the new car and light truck fuel economy tracked the standards for the next 45 years. And you can see some evidence here that the fuel economy was increasing before the standards actually took effect in 1978. They were passed in 75, but they took effect in 78. Of course, there's more going on here than that. If you look at the spikes in the gasoline prices, those came basically just before the standards were enacted. And a case can be made, I think, that gasoline price caused the fuel economy standards. So the gasoline price shocks anyway. But I also want to point out, and we'll come to this later, that there were more than gasoline price shocks in the 70s. There were gasoline shortages, and I'll come to that later. So those were the new cars, and the new cars and light trucks got more efficient. But what about the on-road fleet? Well, if you take those new car numbers and you weight them by the number of cars by each model year and how much they're driven and that sort of thing, you can come up with a fleet average fuel economy. And there's a fleet average fuel economy for the official test, city and highway test that the vehicles are certified on. But real world fuel economy has been consistently something like 15% lower than that. So if you discount the test values to an adjusted on-road value and compare them to what the Federal Highway Administration says that vehicles were actually getting on the road in each year, which is predominantly based on vehicle traffic counts and gasoline tax receipts rather than tests in a laboratory, they actually match up remarkably well. And it appears that an improvement on the tests translated into a proportional, about 15% lower, but proportional improvement on the road. So what does that mean? Well, cars got more efficient, trucks got more efficient, and after 1975, the very close tracking of vehicle travel and fuel consumption was split apart. And the amount of gasoline that was saved over that time period, some colleagues of mine and I have estimated, is 2 trillion gallons of gasoline, worth about $5 trillion to consumers, and avoiding 17 gigatons of carbon dioxide emission. So it's hard to wrap your mind around those numbers, but 2 trillion gallons of gasoline is enough to run every passenger car and light truck in the United States for 15 years. I mean, it's just an enormous amount of energy. So some of that, though, is due to the gasoline price changes. Some of it, and most of it, is due to the fuel economy standards themselves. It's tricky to try and separate those, but our estimate trying to separate that is about 20% of that can be attributed to things that would have happened had there been no standards, but the gasoline prices followed the path that they did, and about 80% or so due to the effect of the standards themselves. So that's a lot. So more than that, they saved household money, as I said, $5 trillion. In another study, we looked at how those savings, minus the increased cost of the vehicles necessary to achieve the standards, how that impacted each income quintile in the United States. And what we found was that all the income quintiles saved money over this 1975 to 2018 period in this study. And in terms of dollars, the most money was saved by the highest income group. They have the most cars, they do the most driving, they save the most money on fuel. But as a percent of income, the net savings were greatest for the lowest income quintile and lowest for the highest. And you can see in these numbers, it's a direct progression. And there's a reason for that. And that is that a fuel economy of a car changes very, very little over its lifetime. It's almost as fuel efficient at 20 years old as it was when it was first hit the road. But the price goes way, way, way down. And apparently what's happening here is the depreciation in price at about 10% a year enables people who buy used cars to get a bargain relative to the people who buy new cars. They get the same energy efficiency per mile, but at a lower capital cost. And that may partly explain why the fuel economy standards have been tremendously popular with the public. Strong bipartisan support as long as people have been doing surveys. The National Academy of Sciences report in 2002 reported that they looked at 7 surveys. The approval rating of the standards was 72% to 95%. Other polls have shown not only that the public support is around 70, 80, 90%, but it's very strong among Democrats and Republicans, including a poll done in 2019 by Consumer Reports, the Consumer Federation of America, which showed that still the majority of Republicans, strong majority of Republicans, supported the fuel economy standards, as did independents and Democrats. People like them. And that's partly why many economists over the period have said, well, this regulation is the wrong way to do this. You should raise the tax on gasoline. There's some good arguments for that. But I think there's some good arguments against that as well, which I'll come to. But the main reason is people don't like tax increases. And studies that have looked at why people favor certain standards have found that people like standards that are effective. They work. They're beneficial. They have net benefits. They distribute costs and benefits fairly. They're equitable. They incentivize rather than force change. It turns out that people weren't forced to buy small cars. They could buy small car, large car, high performance car, small performance car, light truck, SUV, pickup truck, whatever they wanted. And the burden is on the industry rather than the individual. And that's the case here. Technical performance standards put the burden on the industry. Why do I raise this point? Well, if you're trying to deeply decarbonize, you've got to have policies that you can sustain over 3-4 decades. And if you have public support, that matters. I don't want to discount the importance of industry support. And that's another question that needs to be addressed, because the standards were stalled for a long time, partly because of low gasoline prices, but also partly because of industry opposition. So these are the kind of standards people like. They like subsidies, they like tax credits, they like regulation of industry and not them. I mentioned about the gasoline lines. Someone said to me that this looks like people lining up to get vaccinated. And yeah, it was about that serious. I mean, imagine that you wanted to buy gasoline, but you might not be able to get it. And so much more than the price of gasoline, it was the shortages and the gas lines that made people think, oh, I got to buy a small car. I just got to do something about this. And so in the early years, from 1975 to 1983, cars did get lighter and they did get smaller. The weight has come back, however, so cars today, light duty vehicles today are about the same weight as they were in 1975, but they have a lot more horsepower and a lot higher fuel economy, as this graph shows. But in the early days, there was downsizing. In the later days, no, there was not downsizing. It was done with technology. And this kind of spaghetti chart here shows some waves of technology, certain technologies like fuel injection and variable valve timing and transition improvements, multi-valve engines, and so on, coming up to the present time, additional gears. In 1975, most cars and trucks had 3 gears. Today, it's more like 8 or 9 gears. That allows the engine to operate at its more efficient range most of the time. Then later with the new standards, we get turbocharging, we get stop-start systems, we get these multi-gears, and then also a little bit at the bottom, hybrid electric vehicles and plug-in electric vehicles. But it was, oh, I want to say one more thing about the dashed line there. Essentially measures the efficiency of the engine power plant itself. It's the amount of horsepower per engine displacement, per size of the engine, the cubic inch displacement. And that just improves steadily year after year, and is now improved by about a factor of 3. So you can get the same horsepower today out of an engine that is 1/3 the size of an engine in 1975. Amazing. And you would say, okay, there's a lot of thought that, well, you use up the technology, you'll use up all the low-hanging fruit, sorry. Well, here are curves of cost versus fuel economy improvement over the base year, and it shows the base year in the non-parenthesized numbers on the right-hand side. And the studies from 1990 on are now done by the National Academy of Sciences. The earlier ones are Department of Transportation and other sources, just NAS had not done any studies back then. But they all share one thing in common. There was always, in every one of those years, additional low-cost fuel economy technology available. So the technology kept improving, and the tree kept bearing new low-hanging fruit. And that's why since 1983 on, essentially all of the improvement in fuel economy is due to advanced technology, not changing the characteristics of the car. Okay, so we saw there were net benefits to fuel economy standards historically. The rulemaking for the 2017-2025 standards, which called for almost a doubling of fuel economy, showed that most of the benefits would come from fuel savings to consumers, and that fuel savings minus costs, these are essentially the technology costs for making the vehicle more fuel efficient, since all the rules after the first one were based on what could be done with technology that didn't change the performance or the size of vehicles. So the cost of that technology was by far smaller, about 1/3 or so of the cost of the value of the fuel that would be saved. Well, economists would say that's impossible, because the market is going to find the best combination of fuel economy and cost and other attributes of cars. So there's something wrong with this calculation. But that's what it showed. They would say this can happen. But as it turns out, it can happen. Now I'm going to spend some time talking about why. So sometimes this fact that there's seems to be in many engineering economic analyses, whether they're for buildings, whether they're for appliances, refrigerators, home heating, industry, there seems to be always a lot of technology around that can be used to improve energy efficiency at a cost that is less than the discounted present value of the energy saved. And this has been called the energy paradox because it seems to be a paradox from the point of view of efficient markets and rational consumers, or the energy efficiency gap, which I think is more descriptive, actually. So what was wrong with these studies? Are they overly optimistic about technology? Did they underestimate the cost? Were they overlooking hidden costs, like maybe consumers wanted more horsepower and they would value that more than fuel economy? Or are they essentially correct? And the answer to that question depends critically on how markets for energy efficiency actually work in the real world. So this brings us to some insights from psychology and behavioral economics, behavioral psychology and behavioral economics. So here's a quote from Daniel Kahneman, a behavioral psychologist who won the Nobel Prize in economics in 2002. And this is from his book, Thinking Fast and Slow. He says, to a psychologist, it's self-evident that people are neither fully rational nor completely selfish, and that their tastes are anything but stable. Well, these are key premises of the rational economic model. Our two disciplines, economics and behavioral psychology, seem to be studying different species, which the behavioral economist Richard Thaler later dubbed econs and humans. Now, Thaler won the Nobel Prize in economics in 2017. There is only one study that I'm aware of that has ever tried to figure out how consumers actually think about fuel economy when they buy cars and how fuel economy influences their vehicle choices. And that study was done by two UC Davis researchers, the late, great Tom Turrentine, who we lost last year, tremendous loss, wonderful person, and a great researcher, and his tremendous colleague, Ken Karani, both of them anthropologists. So they said, I'm not going to worry about what my bringing some bias is, bringing some theory in here. I'm just going to talk to people and find out how they think about this. And so they started out asking them, well, what was the first car you ever bought? And why did you buy that car? What was the next car you bought? And what did you replace it? And why did you replace it? You know, and just not talking about fuel economy, just talking about how they buy cars and what cars they bought and why, and then gradually bringing them around to talking about fuel economy, then gradually bringing them around to concepts like saving, fuel savings, costs, increased cost, and so on. And what they found was absolutely striking. They interviewed, the design was for 50, 60 households. I think they only got 59. And they were in 10 lifestyle categories. Within those 10 lifestyle categories, they randomly selected 6 households. Some of the lifestyle categories were like recent college graduates and grad students, people in the financial industry, people who bought hybrid electric vehicles, people who did off-road. They were very interesting life cycle categories. But anyway, what they found no household that analyzed their fuel costs in a systematic way in their automobile or gasoline decisions. Zero. Nobody. And they said it's clear that few households understand the financial calculations that lie behind questions about an investment in fuel economy and payback periods. And though even those few do not apply such knowledge in their household vehicle purchase and use. In short, consumers we spoke to do not think about fuel economy in the same way as experts, nor in the way experts assume consumers do. Now, this wasn't a study of the entire US, and it wasn't a random sample. But just think about the odds, even within those life cycle groups of randomly selecting households, and not a single one acted like an economically rational consumer. But that's just that study. However, the people who've been selling cars to consumers for a century, the manufacturers, agree with that. And moreover, the consumers agree with that. So this quote from the 2015 National Academy Studies: during its information gathering process, the committee found that auto manufacturers perceived that typical consumers would pay upfront for only 1 to 4 years of fuel savings, a fraction of the lifetime discounted present value. Depending on assumptions, the lifetime payback period should be like 7 or 8 years. So that's less than half. And so I had an opportunity to put questions on 4 national surveys done between 2004 and 2013. And I asked people the following question. Consider the next car you're going to buy or thinking about buying. They're offering a more efficient engine. It costs $1,200. How much does it have to save you every year in fuel for you to be willing to buy it? Randomly selected half of the respondents got that. And the other half got, it saves you $300 a year. What are you willing to pay for it? And the payback periods, which are implicit, I'm not saying people actually have payback periods, but their answers to this question imply a payback period. And those payback periods were just what manufacturers said they would be, somewhere between 1.5 years and 4 years. And it didn't matter which year. In 1 year, I separated people who buy predominantly new cars from people who buy predominantly used cars, got the same answer. Now here on this graph, NR means non-response. A lot of people just said, I don't even know what you're talking about. Okay, So economists would say that's not the right place to go. You got to go to market, reveal preference, and so on. In 2010, I completed a study for the Environmental Protection Agency, looking at the entire econometric literature and what it said about willingness to pay or value consumers attached to fuel economy. It turned out that about half the studies said that people seriously undervalued fuel economy, and half the studies said they got it about right or overvalued fuel economy. Since then, new studies came out, and many economists said, see, new studies with better data and better econometric methods are showing that people really do correctly value fuel economy. So 2018, I did another study for the EPA looking at the econometric literature and what had happened in between, and found exactly the same thing. We could talk later about why that might be. So are these mistakes of economically rational consumers, or is this normal human behavior? Well, over the years, behavioral economics has identified many ways that people's actual decision-making differs from the rational economic model. Here's a list. But perhaps the most important one is loss aversion. So psychologists say, economics says people have one way of thinking, economic rationality. Psychologists say, no, people have two ways of thinking. They have a system one that operates automatically and quickly with little or no effort and no sense of voluntary control. This is the system that on the one hand decides if an object is flying at your head at a high speed, you should duck. You don't say, an object is flying my head at a high speed. If it hits me, it probably, by that time it's too late. So your reflex, which is not really reflex, the intuition just tells you to duck. And so this is your non-reflective, intuitive way of thinking. System two allocates attention to effortful mental activities that demand it, including complex computations like what's the present value of fuel savings. We think of ourselves as system two. This is the reflective part of the conscious mind that says, oh, I'm alive, I think, therefore I am. But system one, which does most of our thinking for us, is unless we override it, is loss averse. And what does that mean? Well, when evaluating a risky bet, the loss averse mind counts potential losses about twice as much as gains. There's a graph here, which is typical from one study. There have been a lot of studies, and they show up somewhat different results, higher, lower, whatever. And there's certain, and furthermore, these gains or losses are evaluated relative to a reference point, which is the do nothing point or the status quo point. If I don't buy the engine, what? That's the do nothing option. And this perceived value, therefore, is context dependent. It depends on how the choice is put to me. It depends on how the choice is framed. That shouldn't happen to a rational economic consumer, but it's the way real people think. So I'm going to evaluate things one way if it's presented or framed a certain way, and another way if it's presented or framed a different way. And what leads to the framing that induces, what kind of framing induces loss aversion? Well, it's more likely for large amounts of money, hundreds, thousands of dollars. It's more likely for simple, risky choices than complex comparisons. So should I buy the small subcompact, or should I buy the Ford F-150? That's a complex comparison. There are lots and lots of differences between those cars that I need to think about. Fuel economy is just one of them. It's more likely for infrequent choices. If you can learn, your conscious mind can learn how to do this thinking, but if it does it infrequently, it may not bother. And there's no loss of aversion for normal purchases. So just buying a car per se doesn't induce loss aversion, even though there's always risk involved. It's not simple. So do people understand this? Yes, they do. They do understand that fuel economy is a risky choice. Why? The price is known, but the present value of future fuel savings are uncertain. First of all, the car says it'll get 37 miles per gallon, but I know I'm going to get something else. It says right on the label, your mileage will vary. In the lower right hand, this is data from people who reported their fuel economy, what they get, to the website fueleconomy.gov. And we mapped it against the EPA test cycle fuel economy. That's what the compliance says. That's not adjusted for real world. And you can see that the actual reported fuel economy falls well below the real world. In fact, it falls about 15% below. And there are different technologies in here, but similar pattern. But the main thing I want you to see is this huge scatter. There's an enormous variability. And so people are right to be uncertain about what fuel economy they're going to get. And then there's the price of gasoline at the top, which is driven by the price of oil. And statistical analysis has shown that the price of oil is not distinguishable from a random walk. So there is nothing to learn about the future price of oil, really, from that perspective, but it's uncertain. So I took these kinds of things and other factors. I assumed that people were loss averse, and I calculated with this uncertainty, how much would people be willing to pay for a fuel economy technology if they were offered the chance to buy it or not buy it, like a hybrid vehicle or not hybrid vehicle. And I got back the answer that loss aversion alone would account for that payback period being only about 3 years. So this is why I think loss aversion is important. I'm not saying the other behavioral factors and behavioral differences are not important. No, they're all probably going on at the same time. But what we know about this is what the direction is. It's unequivocally going to be for undervaluing fuel economy or energy efficiency in general. And it's going to be large, almost as large or about as large as what we see from consumers, from manufacturers, and could well explain most, if not all, of why people undervalue fuel economy. And not only that, it says it's context dependent. So if manufacturers trying to offer a person fuel economy, they get a loss averse response. But if you have a regulation and you walk in the showroom and all the cars are more fuel efficient, that doesn't necessarily induce loss aversion. Okay. So what's the implication for policy? When markets undervalue energy efficient technology, you can set a technical performance standard. You need to set a technical performance standard or a tax on energy efficiency to get an economically efficient policy. Taxing gasoline alone won't do the job. And there's two very interesting papers. There's a list of references at the end of my presentation. Prove that mathematically, okay? So we've got to have either a tax on energy inefficiency in addition to a tax on gasoline, or you need to have a efficiency standard, a technical performance standard that induces a shadow price on energy inefficiency, either one. Okay, so you can get large private benefits, and these large private benefits will enable you to require efficiency improvements that are well beyond what would be justified by a Pigouvian tax or a tax on the externality alone, the damage of the externality alone, because of the extra benefits of correcting this market imperfection. Okay, so let's come now to the question of, just checking my time. Let's come now to the question of what could go wrong, unintended consequences. And here's sort of the leading issues that have been raised about potential unintended consequences. First, there are hidden costs. People would rather, the main trade-off is with horsepower. People would rather have more power, more acceleration in their vehicles. They value that more than fuel economy. Therefore, you're underestimating the cost by just using the cost of the technology to measure the cost of meeting the standard. Then safety, I mentioned that already. Then the rebound effect, typo there. Anyway, the rebound effect says you make cars more fuel efficient and you lower the fuel cost per mile of driving, people are going to drive more. And then the Grunspect effect, which I don't know, I may never get to that, is because of regulations, if you assume markets are efficient, people are perfectly rational, economically rational, let's say, then once you impose a regulation, you're going to get cars that people will like less than the cars that the market itself would have provided them. That means they're going to buy fewer new cars, and that means the prices of used cars are going to go up. And that means the stock turnover process is going to slow down. And among other things, that means the penetration of safety equipment into the fleet will be slowed, and that's a bad thing. Okay, so trade-off with acceleration. Surely You certainly can improve fuel economy by downsizing a vehicle's internal combustion engine and reducing its acceleration performance. And we saw that from 1975 to 1982, horsepower per pound did not increase, weight decreased, but horsepower per pound did not increase over that period. But from 1983 to 2005, horsepower per pound for light duty vehicles increased at an amazingly steady rate. I mean, that graph shows the average horsepower per pound of a light duty vehicle, sales weighted average in the US, and it is fit almost exactly by a simple quadratic function. Year after year after year, gasoline prices going up, gasoline prices going down. There's all kinds of stuff going on. And yet, all you need is a simple quadratic function, to which I've added the effect of increasing CAFE standards for light trucks and increasing CAFE standards for passenger cars. The trucks starting in, I think, 2007, the cars starting in 2011, and the gap between the gap, which is the increase in fuel economy required, growing over time. And sure enough, we see that this simple equation predicts that, yeah, without the standards, cars would have been even more powerful. So performance was increasing, acceleration was 0 to 60 seconds was decreasing, but not as fast as it would have been, probably, if you believe that this trend would have continued. But it was only about 5 or 6% lower at the end of that time period. And if you use what we understand to be the best estimate of the value of horsepower to people, to car buyers, which comes from the literature, and there's a lot to be said about how accurate it is, and blah, 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 blah. But if you use the mean value from the literature, from meta-analysis, you find out that the foregone cost of the horsepower was only worth about half the actual cost of the technology. So using the cost of technology did not underestimate the cost of meeting the standards because of foregone horsepower. The foregone horsepower was worth less. Okay, safety. So now, people said, okay, cars are going to get smaller, cars are going to get lighter, and in fact, they did in the early years. And I know in a head-on collision between two vehicles, I want to be in the bigger, heavier vehicle, because simple physics tells me that the change in velocity in the lighter vehicle is going to be bigger than the change in velocity in the heavier vehicle. And intuition is correct. Your probability of dying and getting seriously injured increase exponentially with the delta V. Basically, what kills you is colliding with your car, and the faster speed at which you collide with your car, the more likely you are to die or get thrown from the car and so on. However, there's a winner and a loser in that equation. So it's not, from a societal perspective, the answer is not so obvious. And furthermore, if both of those vehicles take 10% of their weight out, there's no change from the original state. There's no change in the original condition. Now that's just for a simple elastic collision, which assumes there's no energy absorbed in the crash. So the formula for energy absorbed in the crash is more mathematically complicated, which is why I didn't put it there, but it gives exactly the same result. Exactly the same result as I described. So, but reality is even more complicated than that. There's single vehicle crashes, you run into objects, you run into objects that break away, you run into objects that don't break away, your car rolls over, there are pedestrians being hit, there are cyclists being hit, there are heavy vehicles that run into you. There's a very large, complicated number of crashes out there. So in the late 1990s, NHTSA began looking at all those complicated crashes and trying to figure out what would happen if you took weight out of vehicles. And after about 15 years of analyses, some sponsored by Honda, some done by LBNL, others done by NHTSA, they finally reached a consensus, which is expressed by this quote from NHTSA in 2012. Basically, the results are non-significant. There's not a statistically significant relationship between taking mass out of cars and traffic fatalities. if you hold the footprint of the car constant, which is essentially the rationale for the safety effects of the footprint standard. And that's what we have today, footprint standard. Okay, the rebound effect. Well, yes, there is definitely a rebound effect. There are some things that often don't get considered. Now, one is, well, we did make the cars more expensive. So the fuel cost per mile is down, but the capital cost is up. How do people think about that? Well, that's a really good question. I don't think anybody's quite answered it yet. But in any case, regardless of that, what we call the direct rebound effect, the effect of fuel cost per mile on vehicle miles traveled, from initial studies, which were based on data from the 60s and 80s through the 80s, said 1% change in fuel cost per mile reduction in fuel cost per mile is going to cause an increase in travel of 0.2 to 0.3%, to a 20 to 30% take back of the efficiency benefits in terms of more travel. But more recent estimates indicate a declining rebound effect over time. There are good reasons for that. If income grows, the value of time is worth more. The value of time is worth more. The cost of the car and the monetary costs count less. As cars get more fuel efficient, the cost per mile goes down, and the share of fuel cost in the total cost of running the car becomes smaller. You know, you imagine it goes to zero, and then who cares what happens to the fuel cost per mile? If your fuel economy is 300 miles per gallon, you don't even care. So there's good reasons why it should go down over time. There are others: saturation of cars, number of licensed drivers, number of cars owned. There's now more cars in the more motor vehicles in the U.S. than there are licensed drivers to drive them. So it's been going down over time, and not only going down over time in the U.S., but a meta-analysis of international studies has been going down over time in the whole world. So it's reasonable to expect that to be going down. And now I think a consensus is more like 0.1%. But there's still some unresolved issues. I won't go into this graph here, but it's different ways of estimating the rebound effect and coming out with very different answers. Now, the Grunspect effect. Well, this is like back to how do people think about fuel economy? Because if people are loss averse when presented with the risky choice to buy or not buy fuel economy technology, but when all the fuel economy of cars is rising, they're not loss averse, then it's entirely possible for the market to undervalue fuel economy technology without regulation, but to value it with regulation. Now that drives economists nuts, okay? But hey, so if that happens, if people really do like the new cars better, then we won't get a Grunspect effect at all. So my point is, this whole thing turns on how the market for fuel economy works, whether there is or is not a Grunspect effect. So what's the role of fuel economy and greenhouse gas standards going forward? Coming to the last part of the talk here. As I said, you need a systems transformation of the global energy system. And that means you're going to need many, many different kinds of policies, in which California has really been a leader in the world on that subject, trying to address as many of those as they can. But if you improve fuel economy, you will reduce the emissions from the internal combustion engine vehicles sold before the goal of ZEV, 100% ZEV is met. That's presumably where we're going in order to achieve deep decarbonization. But let's say for the next 15 years, we're going to be selling a lot of internal combustion engine vehicles. If they're more efficient, and just making them all hybrids could make them 50% more fuel economy and at least, and 33% less greenhouse gas emissions, that's a good thing. Also, we got to decarbonize fully the electricity grid around the country, and that'll take time. And maybe those things will match up exactly, and maybe they won't. And also, we know that strict standards induce a shadow price. And inducing a shadow price on vehicles for inefficiency means it's going to favor the most energy efficient vehicles available, and those are the battery electric vehicles, and to a lesser extent, the fuel cell electric vehicles. So now we're inducing manufacturers to price those vehicles to sell more BEVs and to sell more fuel cell electric vehicles. And finally, as I said at the very beginning, there are advances in non-powertrain technologies, materials, lightweight materials to reduce vehicle mass, the accessories, aerodynamic drag, rolling resistance. These will benefit all vehicle types. And finally, if we if we improve the energy efficiency of internal combustion engines, then if zero carbon liquid fuels are a part of the solution, and this is probably more relevant for medium and heavy duty vehicles than it is for light duty vehicles, then it's a smaller problem that those fuels are likely to cost more because we don't use as many of them to move the same number of miles. I'm going to go through this quickly because I've run out of time. But this graph just shows, look, if we essentially set the standard such that all internal combustion engine vehicles would have to be hybrid, they might cost something like $2,500 more, then we would get to the crossover point in terms of purchase price for BEVs and fuel cell vehicles faster. And that's the #1 barrier to sales. Also, there's just the uncertainty. Fuel efficiency is to some extent a hedge on the bet that we can get to 100% BEVs quickly. So this is a range of forecasts from 10% in 2050 from the Energy Information Administration, boo hiss, to much higher numbers by other people. But really, we don't know. And the graph on the right-hand side shows that we have a long way to go. So I think this just recapitulates what I've already said before, so I'm not going to say it again. It's there to remind us of the reasons for including fuel economy and greenhouse gas emission standards in the policy strategy that we use for deep decarbonization. And now at this point, I'm happy to take any questions and engage in discussion. So thanks for your attention.
David, thank you so much. That was a brilliant tour of, all the issues associated with CAFE and emission standards. I just want to say one thing is that one of the reasons we invited you is because you are a model for interdisciplinary analysis and research. And that is the essence of what we do in ITS and the TTP graduate program. So thanks for that.
That's right. Well, I'm not saying it's right, I'm a model. I'm saying that's what you do. and
you're a model. Okay, so we have a lot of questions here. Let me start out with the students. Oh, wait a minute, let me get it. Okay, can you stop screen sharing so I can see folks here?
Yep.
Okay, okay, so any students raise your hand or just speak out, I think that'd be fine. Because we have a whole lot of other questions, but I want to give you first shot at David. Okay. So I see, okay, go ahead, Hayden.
Yeah.
And then Trisha will be next.
I love the slides. They were very easy to understand. Thank you. So I've always wondered how we got to the current geometric form of our vehicles. I feel like they're all converging on one optimal aerodynamic form. And I've always wondered why they're so much heavier than the people they're designed to transport. Do you think that the cars are ever going to change their shape or weight? Because I feel like they could be so much lighter.
Yeah, that's a very good question. It reminds me of a talk I heard many years ago by John Haywood of MIT, who essentially wrote the textbook on internal combustion engines. And he used to give this talk where he said, well, what you're really doing is you're transporting a person, and then you have the weight of the vehicle, and then you have the really poor efficiency of the power plant, and so on and so forth. He basically showed that the energy efficiency of passenger car transportation was 1%. 1% of the energy being translated into useful work. And it's better now, but there's still a lot of extra weight in that car, and most of it's empty, and the payload is pretty small. So yeah, I think the reason the cars look the same is aerodynamics. They all want to be aerodynamic, and there aren't that many shapes that give you really good aerodynamics. So they all start looking very similar. I think we'll see more similarity until we have really automated vehicles where the safety of the operation of the vehicle is such that we just don't expect it's going to crash into anything. And in that case, you can start making vehicles really light. And if, you know, if they're taxis just driving around the city, they can be almost any shape because at low speeds, the aerodynamics don't matter much. But I still think for highway vehicles, aerodynamics will control the shape of the vehicle. But they can be very, very, very light. But that's, I think, a long way off because we have to get 2 fully automated vehicles, and we have to be convinced that, okay, this is really, really, really safe. Nobody's going to crash into anybody.
So David, you know, before Tricia goes, you know, Amory Lovins is on the line, and we're going to see if we can get to him eventually. But let me just, he made a comment about there are ways of engineering and designing vehicles to make them safer, you know, absorbing, you know, the physics and the acceleration and so on.
Sure.
So it fits with what Hayden was saying. So maybe just elaborate a little bit.
Okay, well, you know, real safety experts have been saying for a long time that the challenge today for safety is not crashing a car into a barrier, it's crashing a vehicle into another vehicle and ensuring that the designs are compatible and that the energy absorption is as good as you can make it. And I know Amory has done research on that, and for sure it's true. It's just not something that we have done as a society, and there's not I don't think there's a really good excuse for it myself, but you know, we could save a lot of lives by designing vehicles so they weren't aggressive and harmful to other vehicles. Just this is a lot there. I think any bona fide safety expert will tell you, and they will say, I wish that the safety tests were not just crashing into barriers or crashing into limited kind of side impact that we have now. We're trying to consider all the possible crashes and making sure that I think, you know, to some extent it's just the way we think, you know. Oh, I don't have to wear a mask. That takes away my freedom. Oh, I don't have to have a car that's safe for somebody else. I can have the car I want the way I want it. Well, and hopefully we get past that someday.
Okay, we might be coming back to that. So Tricia.
Hi, thank you much for your presentation. And I was curious, I was wondering if you'd be able to elaborate more on econs and humans. Like what would an economist say is the perfectly rational choice?
Right. Well, you know, there's plenty of economists around, and you'll get a much better defense of economic rationality from them than you will from me, but I'll try. So economists would say a couple of things. First of all, that people basically are rational, okay? And that's the nature of human beings. And they would say, you haven't proven that people actually behave loss averse when they buy cars. All you've done is to say, well, loss aversion appears to be universal in this kind of situation. This is the kind of situation with cars. I apply it. I get results that are consistent with other empirical data, but that doesn't prove that people are actually loss averse when they buy cars. You have to give me direct evidence from car purchases. So far, I only know one study that did that. It's a stated preference study anyway, so it's not revealed preference. So that's going to be a main critique. And the other thing I think that mainly that they say is that people don't necessarily have to follow all the steps and calculations in rational thinking. They can intuit it. And I think to my way of thinking, the behavioral psychologists have that covered when they say, If it's something you do over and over and over and over again, yes. If it's a kind of purchase and consideration you do over and over and over again, yes. But when it's an infrequent purchase, probably not. Also, the psychologist's view of the world is much messier. So there's nothing that says that the system 2 can't override system 1, and it does lots of times. You know, your conscious mind can say, well, my impulse is to do this, but I'm not going to do that, right? So it's a much fuzzier world they live in, I think. The first two, I think, are the main economist critiques. You haven't shown that this is actually applies to the specific kind of purchase you're talking about. And the other one is, but people don't have to actually do the calculations if their intuition can do it for them.
So David, let me pull in. So the next I'm going to ask Ray, but before that, there was a question actually, Robert Simpson, had a comment on this, and he said, well, a gas tax would induce savings in usage of vehicle, in gasoline usage, and therefore, which the CAFE standard does not do.
Yeah, that's correct. I don't disagree with that at all. I would say a couple of things. You know, the papers I cited, Alcott et al. and Heudel, both make that point. They say you need both. You need a tax on the externality, in this case on the greenhouse gas emissions or CO2 emissions, and you need a tax on the energy efficiency, and then you can have the economically efficient solution if people systematically undervalue energy efficiency. So you would need both. Now, the point is that the tax on the externality doesn't correct the problem of energy efficiency. And my only point there is, if you can't have the tax on gasoline because the politics won't allow it, are you going to do nothing, or are you going to do the energy efficiency? Okay. Now, I still think we need to have carbon pricing, and we should try to get carbon pricing. And my view is we should collect the revenues for carbon. The government should collect the revenues from carbon pricing and give every person per capita a carbon, what would I call it? Carbon check. You know, here, this is your $300 this quarter for the country's effort to decarbonize. And then people would say, well, you know, I like that. A lot of people would say they like that. Let's make a tax acceptable, because you got to have it for 30 years, 40 years, maybe more.
Okay, so let's have Ray.
Thanks, Daniel. Thank you. It was really informative presentation. My question might be a little off topic. I was wondering if you see someday these technologies and AVs will change the way that we design our street networks.
Change the way we design what?
The street networks.
Business networks.
The streets, the highways, and the street networks. Yeah.
Oh, the transportation networks, the highways and so on.
Yeah.
Yeah. That's a good question. I don't know the answer to that. I mean, you have some real experts there on AVs. And I don't consider that to be one of my areas of expertise. I think that it should. I mean, it's a genuinely disruptive technology, right? If people don't have to drive, and if you can make it completely safe, then you can change the design of highways a lot.
Which causes the less carbons, right? Carbon emissions.
Oh, well, the carbon emissions, hopefully see, that's the reason I'm not an expert. I think the carbon emission problem gets solved by the energy and how the energy is used by the vehicles and what kind of energy carrier they're using. not so much by the automation. There are some advantages that could be realized in terms of traffic control, basically, and vehicle control. But I think those are useful, and we should try to get them, but those are only a part of the solution. And the ultimate solution is changing the energy basis of the system.
Thank you.
Aditya.
Hi, thanks, Dan. Thanks, David. It was a really interesting presentation. I was just trying to understand the green spec effect, and if that is significant, then doesn't that kind of make a case actually for gasoline taxes and measures like that that are not TPS? Essentially, because that in some way probably means that people don't necessarily perceive the value of emissions mitigation coming out of new vehicle technologies as part of their choice making process, which then kind of brings me to the earlier point you had made earlier up in your presentation, which was saying that that TPS puts the burden on industry, and that's the more palatable way to go. But if we are to achieve a deep decarbonization faster, then we might need to do both. And at some point, consumer choice is not really a luxury.
So, yeah, I think ideally we would do both, right? But let me get back to the Grunspect effect. So the Grunspect, Howard Grunspect, I actually know Howard Grunspect, and he was the one who challenged me to do the first study I ever did on the rebound effect when I was at DOE. He later went on to be the head of Energy Information Administration. But the Grunspect effect was a small paper written on tailpipe emissions, criteria pollutants, NOx, hydrocarbons, particulates, CO. And he said, look, you're making the car more expensive, and you are providing no private benefit to the owner because it's a public good, cleaner air. And therefore, people will buy fewer cars, and they will shift their preferences toward used cars, which will bid up the price of used cars. And that slows down the process of stock turnover, and also has some poor equity effects as well. Okay, so the problem with applying that to fuel economy is, number one, there is a private benefit for fuel economy, which is you spend less on fuel. So that's different. And it really comes down to, is it true that you're actually saving money? We showed in our study of income impacts that people were saving money, but we left aside the question of would they rather have had a more powerful car? I think probably not, for a number of reasons. But that's an open question at this point, I think, as to whether people would really have preferred even more acceleration performance than we have now. And they value that more than fuel economy. If they are undervaluing fuel economy systematically in the market, right, then it follows that we already have too much performance relative to fuel economy. You see what I mean? The trade-off has been made improperly. So that's why I said that the whole point of the Grunspect effect hinges on this question of how this market really works. Now, should we have a tax on gasoline? Yeah, we do have a tax on gasoline. It's about 50 cents a gallon, on a nationwide average. That's about $50 a ton of CO2, right? So it would be nice to have a higher tax. That's a road user tax, basically. But some people have said, let's get away from taxing gasoline for energy, for road user fees. Let's tax vehicle miles. I say, no. Leave that tax on energy. We need a tax on energy, right? In fact, what you want to do is index that tax to inflation and index to the average efficiency of all the vehicles on the road. So as the vehicles become more efficient, the tax goes up. And if we double the efficiency of vehicles on the road, now we have $1 a gallon tax on energy. I think the problem with that's also hard to sell. We just have a really hard time getting American people to agree to tax themselves. And I think that if we said, we're going to recycle this, we're going to give it back to you, they say, really? I don't believe it. But if we actually did it and started off slowly and build up and build up and build up, we might be able to do something like that. Or if you hide it, right? So that nobody sees it, and it's implicit tax, that could work too. Could work, but there will always be people saying, oh, it's taxing you, you're going to suffer and you won't like it. It's a hard problem, but I think there are possible solutions. Yeah.
We're going to call that the Greene tax when whenever we get it for multiple reasons.
I wrote a paper on that, and I called the paper "What's Greener Than a VMT Tax?" Anyway.
Okay, so we have a question in the chat from Vishnu, and actually there was a question from someone else as well about comparing a ZEV mandate and CAFE standards. And Vishnu just said, is there a comparative analysis of the two approaches? And someone else just said, which one is better? And as you know, in Europe, they're going the the emission route, essentially a CAFE standard, greenhouse gas route. In the US, we'll see. So any thoughts on that?
I have some thoughts on that. One of the things being part of these National Academy committees is you got to visit manufacturers around the world and ask them questions and stuff. And I would always ask them, why this would be 15 years ago, 10 years ago, 5 years ago. Why are you working on electric vehicles and fuel cell vehicles? And manufacturers like Honda and Toyota and so on would say, well, climate change, greenhouse gas emissions, sustainable energy. We've got environmental sustainability. We've got to do this. And I would then say to them, well, but why are you doing it right now? And they always said, oh, ZEV mandate. And so I think it's really hard from econometric to take an econometric tool and estimate how much the ZEV mandate has changed the trajectory of technology, right? That's really hard to do. But that's what I think the ZEV mandate so far has really been all about. And was the cutting edge driving force around the world in getting better electric vehicles and better fuel cell vehicles. So that's the first thing. That fuel economy standards don't do that. They just don't do that. They do provide an incentive to make and sell those vehicles, but it's not, I would say, in terms of the industrial dynamics, it's not the same as saying, make me a bunch of zero emission vehicles and sell them. That's different, because that gets the engineers working on different stuff, changes of priorities and so on. If I say, just make vehicles more efficient. But the benefit of that is that if the standard is strict, then manufacturers are going to start pricing the vehicles to sell them. And the more efficient vehicles will be subsidized. And see, there's a feature on fueleconomy.gov called "Will a hybrid save me, or can a hybrid save me money?" Something like that. And what they do is they pair the hybrid version with the most similar non-hybrid version. So I did an analysis of that, and I found that the cost of a hybrid in terms of manufacturer's suggested retail price is about $1,750. That has a payback period of about 3.5 years, even at $2.50 a gallon. And yet we're selling hardly any of them. But why are the manufacturers selling them at $1,750 when the best people estimating these costs say, no, it's more like $3,000? So that suggests to me the manufacturers are in fact subsidizing the efficient technology, and they're for sure subsidizing battery electric, or have been subsidizing battery electric vehicles. So the greenhouse gas emission standard or the fuel economy standard does that something for you there. It does something for you in pricing. It's not as much as a $7,500 tax credit, but you know, it's still something. So Zev wins, I think, in terms of getting the battery electric vehicles out there.
So that'll be interesting, right?
I'm afraid.
Can you hear me?
No. Not so well.
Susan, can you take over?
Hi, everyone.
Hi, Susan.
Yeah, so actually, I'm not quite sure where Dan left off. We're doing the outside questions. Okay, did we get the question from Alan?
I don't
Jen?
think so.
Okay, let's go with the question from Alan. And I'm sorry, David, are you seeing the questions in the Q&A?
Oh, I wasn't following them. I will.
Okay, okay. Oh, I guess I should just make sure. Are there any more students who want to ask a question? Anybody? Okay, so we'll switch over to the outside Q&A, but students, go ahead and chat in the box if you want to raise your hand and ask a question. I'll keep an eye on that.
So
okay.
I guess I can ask my
there you are.
question live.
Great.
Yeah, no, actually, I was going to comment that you know, this idea about sort of quote unquote irrational behavior, I think extends even to experts, right? And in being able to calculate even things as simple as you know, fuel savings. So I wanted to ask a question kind of maybe a little bit on behalf of students as well. Maybe if you could talk a little bit about the MPG illusion effect, how that may have contributed to Tom and Ken's study. And then because of that, and this is something that I really don't know, if you're aware of any studies internationally that find differences in the behavior because, you know, the rest of the world uses liters per kilometer.
Yeah, okay, it's a good point. The MPG illusion was identified in a paper in Science, I believe, and they essentially asking people, not revealed preference study, but they found that people's perceptions about what the impact on their fuel costs would be was essentially linear and MPG, which it shouldn't be. So, you know, increasing a car's fuel economy from 45 to 50 will get you much less savings than increasing it from 15 to 20. And that's because it's the inverse that matters, the gallons per mile, not the miles per gallon that determine your savings, fuel savings. And that this was fairly pervasive, they found. And therefore led a lot of people to say we need to report fuel economy estimates in gallons per mile or liters per 100 kilometers as most of the world, or liters per kilometer as most of the world does. And they do it in Canada and Europe and Japan and all over. And I don't know of any sort of revealed preference study that investigated that, whether there was a difference. I do believe, I'm thinking now that there was a study in Canada at least of stated preference about whether this would make a difference, but I'll try to find that reference for you. Right now, I'm not remembering exactly what it was, but I have this vague recollection of a paper.
Yeah, John Axon did a study actually.
Yeah, that may have been the one I'm thinking of.
Yeah.
I remembered it was out of Canada, but I didn't remember.
A UC Davis graduate, I might add.
Yeah, they're all over the place.
Yeah, they are. Speaking of which, we are officially at 3 o'clock. So I think there's some more questions. I don't know if you can hang around and chat a bit, David, for anybody who wants to stick around. But students, let's unmute and do a big thank you to David for taking time out.
It's my pleasure. And I just want to remind you, you're at the #1 place, university in the world for sustainable transportation.
Woohoo! I love that
Make the most of
plug.
Make the most of it.
Yeah.
Right.
Yes. Thank you so much. And we hope we'll have you here in person again one of these days soon.
That'd be nice. Yeah, I'd love
Yeah.
to come.
Okay, so students feel free to take off. David,
you.
if you're
take a
done
while.
for the day, feel free to take off. There were a couple more
Thank
things
you.
in the Q&A if you're interested in answering them.
Only if those guys are still on.
Yeah, there's an anonymous attendee, and then
I see my
Lou-
friend Lou Fulton has got a question. And,
Yeah. I
and-
think
and
there are
maybe
quite a few people still on, so let's assume that these guys are.
So I don't see, when I look at my question and answers, I don't see all of the questions. If you want to send, if you can send me the questions, I see Amory says his question wasn't answered.
I think that's in the, yeah, there's an answer tab. You probably have the
answer
open
4.
tab.
Yeah, okay.
Yeah.
Yeah, do you want me to ask it live?
Yeah, that'd be
Oh,
great.
sure.
David, wonderful talk, probably the best cafe talk ever given, if I had to exaggerate very slightly.
Thank you, very kind.
Yeah. I did a SAE paper about a year ago, sent you a copy recently, that
Yeah,
looks
I
at
remember that.
15 empirical automotive data points, some of them market vehicles, some of them industry designs, showing that integrative whole vehicle design can save lots more, often several-fold more fuel than the standard EPA NHTSA's cost curves show, and do so at lower cost. And that suggests that at least 2/3 of the design space is not reflected in the analytic basis of the CAFE standards. What do you think it would take to change this underscoping of potential efficiency so we can raise our ambition to match what some manufacturers are achieving? And then I had a second question. US happily has switched efficiency standards from weight-based to size-based so as to stop the mass arms race of, you drive an SUV and he'll drive a 18-wheeler and she'll drive a locomotive. That was nuts. But meanwhile, Europe and Japan still have weight-based standards. Shouldn't we be trying to harmonize those before automakers get pulled further in opposite directions?
Yeah, so the second question was a lot easier for me to answer. I think you're absolutely right. I think the choice of weight-based was the wrong choice. I think it's kind of a cultural thing based on who their manufacturers are and what they like to build. And I know that Mercedes for quite some time was lobbying for, and BMW for weight-based and horsepower-based standards. So index to weight and power, because what? They like to sell cars that are heavy and powerful. But those are their customers. But anyway, so I agree. We have the better approach by far, because weight is a really important factor, and sort of taking that off the table as a way to improve fuel. And they have various ways of trying to get around that, but fundamentally, they're trying to fix a problem they created, and not getting all the way there. So anyway, that I agree with you completely there.
And just for reference, the biggest weight saving demonstrated by a major automaker in a 4-seater was, I think, 2007, the Toyota 1X, 70% lighter than a Prius for comparable powertrain and interior volume and functionality.
Yeah, and so your first question, you have been pointing out for I don't know, I wouldn't say years, decades, that sort of drilling through the barrier and going to a completely from scratch design can accomplish a whole lot more than incremental change. And with fuel economy standards and even with gasoline taxes and so on, you're going to get mostly incremental change. Yeah, I think that's true. How do you fix that? You know a heck of a lot more about how, I mean, you have thought so much more about how you fix problems like that than I have. Talked with industry and so on about it. So I'm not even going to try to tell you how to do that. My only thought is that there could very well be a synergy between automated vehicles and this new design space. That if you can have a vehicle you can control so well that it's not going to crash into anybody, nobody needs to worry about that. It's whole disruptive technology. Maybe then, the industry would say, well, why don't we just design it this way? And you can see some thinking around that in the industry, but that's my only thought. And and the rest I would listen to what you said, not what I said.
And then Lou, do you want to ask your question? But maybe we can keep it short and let David get off to his weekend.
Am I unmuted?
You're unmuted. We can hear you.
Okay, and David, you can't see my question. How are you doing, David?
I'm fine. I
Ready?
think your question is in the open section. Yeah, Lou, I'm doing fine.
Good. Ready for the weekend? And so we'll do this quickly. So I mean, what do you think about the Biden administration? What should they try for to 2030? It seems like we have a chance to be quite ambitious here, but what's the trade-off between promoting ICE fuel economy and promoting ZEVs as part of CAFE, reform or CO2 standards?
Yeah. So I try to make the argument that making CAFE tighter does promote ZEVs. It's not as effective as a direct subsidy for ZEVs. It's not as effective as a ZEV mandate, but it does induce a certain amount of subsidy if the standard is tight. So I think the standard for 2030 should be at a minimum of 50% improvement in fuel economy over where we are. Why? You can just do that with hybridization right now. So you should be able to do better than that. And so I would ask I would ask EPA especially to do the analysis. I think with Steve Cliff at NHTSA, I'm expecting they'll get on the ball really fast. But anyway, I would ask those agencies to do the analysis of what can be done if we make by 2010 all vehicles hybrids, all ICE vehicles that are not plug-in vehicles or fuel cell vehicles. If we make all of those hybrids, we should be able to get better than a 50% improvement in fuel economy. So we should ask for something better than that.
I think, and if you look at the EU, that maybe the argument over there is everything you go beyond that, if you ask for 80% better, it's all going to have to show up in the form of ZEVs. So that's where you get a strong ZEV push.
Yeah. So you need to go beyond what can happen there. Now, the laws are a little, the CAFE law is a little bit screwy in that the CAFE law says in setting standards, NHTSA cannot consider the impact on what's achievable of alternative fuel vehicles. And that should be changed. EPA is not subject to that constraint. So either EPA goes off and says, well, we are going to consider what can be done with plug-in vehicles, and we're going to set the standards higher, assuming that by 2030, pick a number, percent are ZEVs. And NHTSA, for some reason, the law was written not to allow NHTSA to take that into consideration. There may be ways around that, but it may well require that the Congress change the law.
Yeah,
but if they don't, then I think they should say, okay, enough of the harmonization. Just EPA, go for it.
Great, thanks. Yeah, very interesting. Yep, we'll see what happens.
Okay, great.
All right. Thank you, David.
Okay, my pleasure. And have a great weekend, everybody. Take care.
Yeah,
Be safe.
you too.